we were talking about black body radiation. And so what you're going to see here is that we want to really get the physics of why classical physics failed. And the black body radiation problem is one of the thorniest of the problems. The next two are much easier. So we want to go through and actually sort of like review where we were last time. So let me go share my screen. And here's what we have here. So one of the things that we see here is that, note that even though it's called the ultraviolet catastrophe, I typically like to call it the infinite energy problem, because that's really what it is. I think the ultraviolet catastrophe, sort of like people kind of say it, but they really don't know what it means. It's the infinite energy problem. If you turn on your oven, the way it operates here is that as you raise the temperature and your oven is heating up, it should eventually put out an infinite amount of energy, which is crazy, of course. And what we found here is that when we looked at classical physics and we looked at the intensity of the radiation, what we see here is that we're seeing this curve, this red curve. So the green curve is the radiation curve from experiment, the black body radiation curve it's known as. And then this Rayleigh-Jeans law, which is the best that classical physics could do, is this red curve. And you could see that right here, this thing it's moving towards infinite energy emission. So it's emitting an infinite energy towards shorter wavelengths. So Planck did what? He parameterized the curve. He really looked at two curves, two theories, Wien's law and the Rayleigh-Jeans law, and he essentially says one works good at low wavelengths, one works good at long wavelengths. And he essentially spliced them together because he was a first-rate mathematician. After he derives the equation, then he asks the question, what does this mean? The bottom line is physics. And so here's what he does. When he parameterized the curve, he realizes that the solution must look as follows here. That the energy is quantized. That the energy emitted by the atomic oscillators comes in little discrete lumps or bundles. That's what they call a quanta of energy. Okay, so the language doesn't exist yet, but this is what they mean by a quanta of energy, or a quantum. Maybe I should say quantum. Okay, it's a quantum of energy. And that is the first time quantum actually really came into play.
What's the year?
This is 1900. And the atomic oscillator, this is a really bizarre thing. I don't think you guys really grasp this, because this is about the most counterintuitive thing you could possibly imagine. So you have this atomic oscillator who's oscillating smoothly, nice and smooth oscillations like a mass on a spring. It could only emit or absorbs energy in these lumps, which is kind of bizarre. I mean, so if I was to kind of think about this in a picture-wise, as an analogy, imagine that you have an oscillator, okay? And here's the oscillator. So when I'm thinking about this oscillator here, what you're doing here is that you're going to want to make this oscillator go up and down. So you can imagine that you have wads of gum. I don't know. Maybe you're chewing cherry gum. I don't know. I don't chew this shit, so it doesn't matter to me. So what you find here is that you're going to throw these into lumps. So if you throw one lump, let's call that E1, then this thing starts to oscillate. So then this guy then oscillates like this. Then if I throw another lump, I don't know, let's say this is a green lump, but this time this lump is very specific. It's twice this. So what does it do? It oscillates up and down. So remember, I'm calling these lumps of gum. So question, what happens if one throws a 1.5 lump of gum? According to quantized energies, nothing happens. The oscillator doesn't go up and down. It stays stationary. There's some serious shit here, right? You throw one lump of gum that has, let's say, mass 1. You take a second lump of gum that's twice the mass, you throw it, it has more energy, right? And then you take a third one and you throw it, it oscillates with a bigger amplitude. But if you throw 1.5, 2.2 lumps of gum, nothing happens, right? Nothing happens. If I was to do that to you and say that, oh yeah, this is reality, I'm expecting that you're going like, that's bullshit. You're probably looking at me going like, dude, this guy's like really lost it or something, right? There's some shit going on that Carlos must have smoked something this morning and he's like really out there. Unfortunately, this is reality. This is the start of this shit called quantum mechanics that if I do it right, you'll never be the same. I promise you. Man, I've been at this shit for 43 years, 45 years. Well, the good thing, I get to share it with you. So now you could be yours here. So this is what this is saying. You have this atomic oscillator. What does it mean to be a black body? The energy that it emits is also the energy that it receives. So when this is emitting radiation into the oven cavity, it's only in these lumps, never 1.5 lump or 2.2 lumps, always discrete integer values. And that's the minimum that it could do. So if it's oscillating at the red lump, then that means it's only emitting and absorbing those at the same time. So you got to be careful here because you're going to see what textbooks say. They're going to say the electron absorbs the energy. If it absorbs the energy, then you change the mass of the electron, but mass is an invariant. So electrons don't absorb energies, atoms do. Don't get caught up on that chemistry shit. That's wrong. Now let's go with the tiny oscillator. So that means each oscillator has this minimum energy that it can emit. And it can emit multiple of these guys, but it can't have a zero value. But it's always emitting that same quantity of lumps. Okay, because it has a fixed frequency for that specific color here. then for the first time, Planck comes in and says that the energy is proportional to frequency. By the way, this was never, ever connected to each other. In hindsight, it should have been. But it wasn't before. So when he parameterizes the curve, he actually sees that there's this frequency dependence, and this Planck's constant is a new constant of nature. And it's super, super important. And I'll summarize this a little bit later, but this constant H, what it essentially tells us, the most important thing about the black body radiation, or the photoelectric effect, or Compton scattering, or the Bohr model, it doesn't really matter. The most important thing is that this constant H is telling us that there's an exchange between an atom and the radiation field, or the light. As light and atoms exchange energy, that constant H essentially tells us how these guys actually exchange energy. And I'll come more into this later, but that constant H is at the core of this whole discussion. So if I have a higher frequency, the tiny oscillator is going to emit a higher minimum energy. So if I have violet light, I get higher frequency, higher energy. If I have a lower frequency one, that tiny oscillator is only going to emit this lower minimum energy that looks something like this. Okay, so these guys are essentially absorbing and emitting these bundles of energy, these packets of energy, these lumps of energy, however you want to call it. And so before we go into the Planck's resolution here, the thing that you're seeing here is what I showed you last time. There's a lot more low frequency. And you could see that classical theory explains, right? Look at the curve. It explains the curve really well down here. So classical physics explains low frequency radiation very well. So Planck, being the genius that he was, is that he did what? He says, the problem with the radiation problem, the infinite energy problem, is this infinite energy. So it's these high frequency oscillators. So in the back of his head, he goes, nature is somehow suppressing these high frequency ones. That's what he's going after. So here we go. Let's finish this up now. So now I'm going to give you a summary. Okay, summary of Planck's results here. There's a piece of me that wants to go in and actually explain all of the physics beforehand, but I think I'm going to break it up into pieces. Planck knew, by the way, you can read it in his writing. I only read it in translated version because he only wrote German. But what you find here is that I'll give you the physics, and then I'll only write down the mathematical expression to show you what he did here. So the first thing he does is that, let's start with the physics explanation. So in the physics explanation, he says something like this. So remember, the picture that you gotta have in your head is the oven, right? So maybe we should draw the oven just to make sure that we're talking about that. Right? So in here, we got the walls of the oven. So when I'm looking at my oscillators here, my oscillators are going to be right here. And then I'll have a red oscillator right there. So you could imagine now that I have these two oscillators on the other side. So as the heating goes into heating up the walls, right? So now you're heating up walls. So that means temperature comes into play. As you heat up these walls, these guys oscillate. And what do? They throw out this packet of energy. And as they do, the red one oscillates back and forth. Now, as these guys are being thrown around, you're going to see is that every once in a while, one of these little packets is going to get what? Is going to hit one of these atoms. So here, what you're seeing here is that this is that they're emitting radiation. And then right here, they're absorbing radiation. Okay? And what happens here is that in here, you get what I call the radiation field. So in here, I call that the radiation field. And what I really mean, it's the electromagnetic radiation, right? When you turn on your oven, you have a magnetron. What does the magnetron do? It makes a little electrons go around in a circle. What do the electrons give? They give off microwaves. So inside your microwave oven, you have a microwave field, a radiation field. So now, here's his explanation then. He says this, for very high frequencies, the energy needed to do what? Resonate. You have to resonate the oscillators in order to make them oscillate. Remember, the string, it's a resonant frequency condition that we set here. Okay? So at very high frequencies, energy is needed to resonate the atomic oscillator. And what you're finding here, so when you look at this, look at the minimum energy now. The energy required is huge, right? So if you think about an X-ray or a gamma ray, those frequencies are very huge. So what you're finding here is that you get a huge frequency that resonates, right? The resonant frequency that resonates this oscillator, that energy is huge here. So Planck looks at that radiation curve and look at the green curve right here. There's very few of those. So what you're finding here is that there are very few high energy atomic oscillators that will emit / absorb, E min. And so what he's saying here is that when he says very few, This is where the suppression factor comes in. So he hunts for a suppression factor. Okay, as he hunts for a suppression factor, what he finds here is that, so then he goes in and he derives a distribution function. And this distribution function, turns out it looks something like this. So if you look at it in terms of wavelength and temperature, remember the black body depends on temperature. And what you find here is that you get a relationship that looks something like this here. And you get something that looks when you take the limit of this going to high frequencies or low wavelengths, this thing essentially dies off. It becomes very, very small. So this implies here that if you take the limit as lambda gets small, this thing goes small. So what it does here is it suppresses those high energy, quanta that are being done here. So think about it this way, but think about it physics-wise. Okay, if you're thinking about this physics-wise, so if I was to use an analogy, think about your oven. Think about your oven. Your oven, heats to 400 degrees Fahrenheit. At that temperature, what do you get? You get mainly infrared. You don't get visible light. So when you look at the curve, it's all in the infrared. Now, if you have like an electric one, you could actually see some visible radiation given off by the iron coil that's in there. But look at the radiation curve. This radiation curve does not go to zero. There's a piece that actually goes into the X-ray and gamma ray region. So what that means is that, believe it or not, your oven also emits some X-rays too. Because it emits some X-rays. I thought X-rays were dangerous, right? They can go right through your body. But the problem is, the radiation curve here tells us that those X-rays are getting suppressed. Planck wrote down the expression that suppresses them with this distribution function. So that's kind of crazy when you think about that. That Planck's relationship proves that you do get some X-rays in your oven, but not that many. If you only get a few, it's not a big deal. So then we go to the second piece here. So now at low frequencies, there are numerous atomic oscillators. And that makes sense here because if you're mainly getting infrared radiation in your oven, most of the oscillators there have to be what? In the infrared region. at low frequencies, there are numerous atomic oscillators that emit / absorb tiny amounts of Emin. However, all of these energies added up, because it being so tiny, don't account for very much here. So then this tells us here is that they each have so little energy that they don't amount to much. So where is most of the energy being emitted at? Well, look at the curve. You could see that most of the energy is where? In the mid-range right here. That's where most of the energy is being emitted. So when you look at Planck's relationship, where does that distribution function maximize? When the temperature is right, it's then going to give you that spread, that spectrum, where you get that. So only the mid-range frequencies have plenty of atomic oscillators. Now remember, in the classical theory, all of these oscillators had the same. They had the same probability of carrying equal energies. But Planck's relationship forces that the most oscillators are in that mid-range, right? Only the mid-range frequencies have plenty of atomic oscillators to absorb energy here. And so when these are added up, they produce the peak of the radiation curve. And that's really the key right there. So he solves this problem by suppressing the high frequency or low wavelength oscillators and maximizes the mid-range oscillators that form the peak. And so by doing this, we could then say, what did Planck actually do here? It's the quantization of the fundamental energy that puts the restriction on the amount of energy that oscillators can have. So the key point here is that it's the quantization of the energy that puts restrictions on the amount of energy an atomic oscillator can have. It's the quantization. That's the important thing. And that leads to the finite energy instead of the infinite energy issue here. Okay, and that's the thing that's most important here. So when I think about this, one of the things that we're seeing here is that the most important thing, if you're going to walk away from anything from this, right, is this: a black body emits and absorbs quanta of energy. Okay? It absorbs and emits quanta of energy.
I
And
think you
so
meant
what,
to add emit/absorb to the last sentence.
say that again? Did I forget?
To the key point. It's a bit of a hanging sentence.
Okay.
It needs a punchline.
Yeah, emits and absorb. But the key thing that you really want to walk away from is that the black body emits and absorbs quanta of energy such that they stay in equilibrium. But the most important thing here is this, that there is some exchange, right? There's some exchange between atomic oscillators and the incoming light. It's this exchange that's at the heart of the issue. Okay? That's the important point. That this energy that Planck says is quantized, it's about how light and matter are interacting with each other. And the only way they can interact is by exchanging quanta of energy, not any other way. And I think that this here has to be the most disturbing piece of all. It's like the gum analogy that I gave you, right? It seems so bizarre, but that's really at the issue here. So before this, everybody believed energy exchange was continuous, right? I mean, think about driving your car. If you're driving your car and you want to go from, so what I mean by this, maybe I should do this as an analogy as well, because I don't have the language for this. Imagine that you're driving a car speeding up from, let's say, 50 miles an hour to 70 miles an hour. Let me ask you a silly question. How do you get from 50 to 70, right? You go to 50.1, right? Or you could go to 50.00001, 50.00002. Or if we just do increments of 1 mile, we go 50, 51, 52, 53, etc. Well, That's a continuous, if we now translate it to kinetic energy would then transfer continuously. But in the world of quantum, would you be surprised if all of a sudden you're going 50 and you stepped on your accelerator and now you instantly go 55? You didn't go 51, you didn't go 52 or 53 or 54, you went 55. And then you press on it a little bit harder and then you go to 60. Right? You would be quite surprised if you sped up or you speed up in 5 miles per hour increments. Oh, that's spelled wrong. That's okay. So you'd go 50, and then all of a sudden 55, all of a sudden 60, etc. My question is this: what happened to 51, 52, 53, 54? In the quantum world, they don't exist. So if I have quanta of only 5 miles an hour, there is no between. So when we're now talking about these atomic oscillators, and let's say I have this oscillator now, and this oscillator is doing what? It's oscillating. That means I'm throwing these little bundles of energy of only increments of E minimum. That's what makes the oscillator. So I can throw them like this, but if I try to throw 1.5 E min, you get no oscillations.
So Carlos, to go further into your analogy, let's just say I had a car standing and I hit that car at 51 miles an hour. Would that mean that that car just doesn't move at all?
That's right.
Okay.
No. It
And
would
then-
continue. No, wait. It would continue to move at 50 miles an hour.
Okay.
So
Yeah.
even though you push the gas and you're going like, okay, I'm going to go to 51, you don't do anything. And it's sort of like this. If I throw a lump that's one of E min, then it makes the oscillator oscillate. So now, oscillator oscillates. But now, let's say I do this now. I take another lump and I throw it, and it's 1.5 E min. You get no oscillations. And you got to admit, that's a bit odd. In fact, I don't even think Planck ever accepted this, by the way.
Does that not like violate conservation of momentum? Or am I just thinking about it?
No, because then what you're gonna, I mean, I could get my picture to go like this instead. Make it oscillate like this. So then momentum will not be violated.
Okay.
But it's customary to look at that because the waves that are produced for light is transverse, so it has to be perpendicular to the direction of the oscillation. So Planck never accepted this. He thought that once the energy was emitted in these bundles, it then goes into the radiation field and it's smooth. Okay, so Planck never accepted his theory. Now, I should be careful when I say never accepted. You got to listen to his words carefully. So for part of the time, he would go like, okay, it must be true because all these experiments are showing that. But when you listen to what he writes, though, he's saying there must be a way around this. So even though he's saying publicly, yes, this is true, there must be a way around this. And so he just said this here. So here's the key thing. Planck never accepted this theory and believed that once the energy was emitted, the so-called bundles combined to somehow form smooth waves. And I think this is a very important statement right here. Okay? Definitely the thing that I'm talking about, this is the important piece right here. And you'll see that a lot of textbooks miss that. But when you start to get more deeper into quantum mechanics, you'll see that it's the interaction that's the most important piece. So Planck says he never really accepted this, and he believed that once energy was emitted into this bundle form, into the radiation field, they somehow combined into smooth waves, very similar to discrete water droplets falling into a tub. And if you get enough discrete water droplets, then you have water, a body of water that could now have waves. That's the way he thought. Unfortunately, that's not the way it is. Enter Einstein. This SOB really caused a ruckus. Okay, so this is 1905. Okay, 1905. And here's what you find here. So Einstein enters the picture, right? So Einstein comes in with the photoelectric effect. And what you find with the photoelectric effect, here's what Einstein says. He generalizes, if I could say that, he generalized Planck's quantum idea. By arguing, that the electromagnetic radiation, the light, the electromagnetic radiation retains its quantized character. Even in the radiation field. Okay? Even in the radiation field. So what's he really saying here? So this quantized character, even though it wasn't called the photon then, this is the origin of the photon right here. And even though I think his general theory of relativity is the most impressive theory I have ever laid eyes on, I have to say that the photon idea is probably his greatest achievement. I just think it's his greatest achievement. I don't, in my mind at least, I know other people will argue differently, and that's okay. We still struggle with the photon today. And so he stresses that the photon exists in 1905. Nobody believes him. In fact, I think it wasn't until like 1919, 1920, or maybe it was 1921, when the photon was without any doubt experimentally verified, that people started to accept the photon. And that's essentially when he won his Nobel Prize, even though he could have won it for numerous things. But he essentially went 15 years with nobody believing him, but a handful of people. That is impressive. Okay, here we go. Next topic, photoelectric effect. The photoelectric effect is the easiest way to visualize why classical physics failed. This is the easiest to see why classical physics failed. Okay, without a doubt. The photoelectric effect is light-induced emission of electrons from a metal here. Okay, so when they say the word photoelectric effect, this is what they call light-induced emission of electrons from a metal surface. Now, Hertz was the guy who actually, like when you think about Hertz, like 60 Hertz in your outlet, Hertz, that guy was the guy who discovered it accidentally. And he discovered it somewhere around 1890. And the thing that's most important about the photoelectric effect here, right? So Hertz, amazingly, and I really mean amazingly, showed that dim light shined on a metal could eject electrons. And dim light, I should have capitalized that. He amazingly showed that dim light could eject electrons. What's the main point here? It shouldn't happen in classical physics at all. There's no reasonable explanation why the wave model of light could eject electrons. So what's amazing about this is that it's this. It shouldn't happen at all via wave model of light. And remember, back up here, the whole thing was what? The exchange between the atomic oscillator and light, right? We're thinking waves, but now we're saying that Planck is telling us, but wait a minute, there's a problem with this exchange of energy. So now we're looking at the same thing. We're looking at exactly the same thing. What is the exchange of the atomic oscillator with light, which we all know is what? A wave, especially at that time. So the fact that it happens is the most important thing. Everything else is details, important details, but that's the most important thing. That's the thing that I want you to walk away. So if you think about the photoelectric effect, it's this right here, that dim light knocks electrons off of a metal here. So what you find here is that, so what's happening here? So physically, what do we know here? So what happens in the photoelectric effect? Okay, that's really what we're trying to answer here. And so what we want to do here is that we want to look at the setup here. Okay, so let me go bring in this. So let's say that this is my photoelectric effect apparatus here. So what you find here is that right here, what you're seeing here is that this guy is my light source. So that means I could come in here and I can shine light. And as I shine light, I know that light then is going to go onto what? A piece of metal. So then right in here, in this vacuum tube, I have a piece of metal. Now, when you shine light, what we know about metals here is that metals have weakly bound electrons. So old thinking is that the light coming from from the light source, then they'll tell you, and even by the way, I think even Albert Einstein said this too, that the electrons absorb the energy. Well, that's not true. They excite the atom. Once I have an excited atom, the electron moves higher in electrical potential energy, and it can eventually get out of the potential well here. And I'll explain that a little bit later here. So now what happens? So if you think about this, we should think about it in a little bit, think here. So when we should say here that when light strikes the metal, right, energy is absorbed by the atoms. So if I get energy absorbed by the atoms, now I have an excited atom. And if it's enough, I can then eject an electron from the atom. Okay? I can eject a metal from the atom. Now, what I want to do here is that I want to come in, and now here's what you find here. So if I have light, what you're going to see here is that then I get these electrons that are being shot out, right? So I have these electrons that are now moving off the metal. And so these electrons are known as photoelectrons. Why do they call them photoelectrons? Because it's light induced. And then what you have over here is that they're collected here. And sometimes you'll see that they'll call this the collector. And what it really does here is it measures current. So it's a glorified ammeter, if you know what that is. It measures current here. And so what you're finding here is that what we want to do now is that let's look at some of these details here. So what you find here is that if I was to think about what do I mean by energy absorbed? Well, think about you and the sun. If sunlight comes, and it lands on your skin and it's warm outside, what does it do? It warms up your skin. If I shine light onto a piece of metal, what's it going to do? It's going to warm up the metal. If you shine this light and warm up the metal, sometimes you can eject electrons from it. But it has some very strange features, though. Right? Here's one. So let's think about this. You would think that if the light intensity that is the brightness is increased, then that means you would expect here the speed of photoelectrons would also increase. Right? If I increase the intensity of the light, you would expect that the speed of the electrons coming off would be faster. The answer is no, that's not what happens. Right? What you find here is that the number of electrons increases, but not their speeds. Now that's really surprising here, because you know that if you're on a really, really hot day, and let's say you're wearing a black shirt, you warm up quite faster with the black shirt than you do with the white shirt. That's because the black shirt is absorbing more heat from the waves here. But that's not true with the photoelectric effect. So one of the things that we can do here is let me see if I could turn this guy on here. Oops. So what I'm going to do here is that I'm going to share my screen with you. And let's go look at this photoelectric effect thing. So right now I have this set at violet light. So if I turn this guy on, what you're seeing is that I shine it and you can see that electrons are coming off here. Now note that there's various speeds of the electrons, and I'll explain what I mean by that. But what you'll find here is that I can control how fast these electrons are going if I, excuse me, not how fast, but if I increase the light intensity. So you kind of have to you could see that some of them are going fairly fast and some of them are going slow. But now look what happens. If I increase the light intensity, I get more for certain, But what you're seeing here is that if I look at the fastest ones, it looks like the fastest ones are not like going much, much faster. It looks like they're going about the same speed. And there's a way to measure this thing. And I'll show you this in a minute here. And so
What's the battery for?
yeah, that's exactly what the battery is for. And so what I want to do here is that I want to show you what the battery is for now, is that when I come back to my screen here, this guy here is a battery. And what you find here is that electrons have a negative charge. So if electrons have a negative charge, so what you find here is that now you test this by charging the collector plate to a negative value. And so what you do here is that now that I have little electrons that are coming here, what you'll find here is that if I have these electrons, I know that they have a negative charge. So if I make the plate negative also, that means I'm going to put a bunch of negative charges on this plate. As these guys are coming in, what you're going to find here is that these electrons do what? They're going to get repelled by the negative plate. Well, it turns out that this is a problem of potential. And what you find here is that if you were to look at the energy picture, so from Physics 4B, I know that some of you have not had Physics 4B, but it's okay, because it turns out that the parallel plates, so if you have two parallel plates like this actually looks almost identical to gravity. And so if you look from 4B, you have an energy picture. So if I look at the energy picture of what are these called parallel plates, here's what you get. What you find here is that these electrons are moving up an incline. Okay? They're moving up this incline. And so when you're looking at this guy here, this represents the electrical height of the parallel plates. So you could imagine that if I have my little electron here, so as I have this little electron, what I'm going to do here is that I want it to reach all the way up to the top. What's up at the top? This negative plate. And so if you shoot this electron and you ask the question, how much kinetic energy do I have to get this electron up here? What you're going to find here is that you're going to say, well, to get to the top of the ramp, I need this amount of kinetic energy initially. And that means that the maximum energy that I can have is up this ramp, which looks like a gravitational potential. And so when the electron reaches all the way up to the top, we're going to say that it has done what? It has lost all of its kinetic energy, and now it has what? All potential energy. So when you're looking at this potential energy here, you're seeing here that this is electrical potential energy. Okay? And so what you're finding here in this situation, that means that if this is maximal kinetic energy, then the electrons almost reach the very top. In other words, that the electrons are stopped by the electrical ramp. But the electrical ramp is the electrical potential. So that means then, if I now change, so now let me go show you what I mean by this. So if I now go to this plate here, what I'm going to do here is that I'm going to make this negative. So now look what happens when I make this negative. Are you guys seeing the applet? Okay, so now check this out. If I make it negative,
Oh,
so let me not, how about if I do this here? So note that here it's at negative 0.8, so that's too much. How about if I do, 1? So if I do 1, you could see how it barely gets to the very tip right there. Now, what if I made this 0.09? You see how some of them are getting there? So they're going all the way up the ramp. But if I go to, it looks like 0.1, okay. But if I go to 0.1, let's see, do they still get there? Oh, I thought they weren't getting there earlier. So then I've got to increase this guy. So if I go to 0.3, what's going on here? Am I not? I thought I had them stopped here for a moment.
You did. I don't. They were stopped when you had it at 0.1 before.
Yeah, that's what I thought. So maybe let's go to 5 here. So some of them are still getting through. So the question is, I just got to keep clicking this thing till I get to the point where I stop them. Wow, this is like,
It's not working.
yeah, I played with the numbers before we started. Let's see. Damn it. Looks like it might be 1 volt. Okay, it looks like 1, see, only the fastest ones get right to the edge. Okay, now look at the intensity here. I'm going to lower the intensity. Now, are there any, there's less of them, but we want to look at the fastest one.
so you're just changing the amplitude.
No, I'm just changing the
Of the
voltage. Oh,
light.
yeah, the amplitude of the intensity. So, God, they look like they're not going. Okay, this thing is really pissing me off here. So if I increase the intensity, let's see if this app works here. It looks like they're all going about the same distance. So in other words, even though I increase the intensity, the maximum kinetic energies of these electrons don't change. Yeah, I don't know what's going with this because it seems like it's variable right in here. But nonetheless, that's one of the things. That's a strange feature. If you increase the intensity, right? If I make the intensity super bright, you would think that the electrons would be coming out faster. They don't. They get the same maximum kinetic energy or the same speed. So let's go to the next one. So the next one here, so that's how you get this thing. So what you find here, so if you have maximal kinetic energy, then that means that all electrons have, not all, excuse me, so if you have maximal, this measures the speed of the fastest electrons, right? It measures the fastest. And what you find here is that these do not change with intensity, which is, of course, super counterintuitive. So if intensity doesn't change it, what does change? So the speed of electrons does increase with frequency increases. So in other words, now I don't know if you understand this, but frequency is about the color of light. It's always about the color of light. And so what you're finding here is that if I have a high frequency, so for example, if I have a higher frequency light, right? In this case, let's say that I'm looking at violet light. Then what you're going to find here is that this guy gets what? I have higher kinetic energy photoelectrons. If I have a lower frequency light, in this case, how about if we just say blue light? That's lower. If you look at blue light, what you're going to find with these guys is that you're going to have lower kinetic energy. So the color of light determines the kinetic energies of these electrons, which is kind of crazy. Because now if you're thinking about a piece of metal, right? Here's this piece of metal here. And so that means if I come in and I shine violet light, right? I shine violet light, you're going to see that the ejected, let's say it's this violet electron, this guy comes out with a higher kinetic energy. But if I take blue light and I shine blue light onto the metal, this guy has less kinetic energy because it has a lower frequency. So how do we see this with the applet here? So if I go into the applet, so let's see here. So this is violet right here. Man, this is kind of, let me see if I can change this one more time. Let me see if that stops them all the way. Looks like they're getting closer. So now look at violet here. Okay, so now let's look at the blue here. So if I change this to blue, I'm not changing the intensity. So I'm saying that if I shine blue light, these fastest electrons shouldn't get all the way there. So now let's check this out. I'm going to go to blue. Look at the distance that they go. They go less. So if I look at this here, they're shorter. And if I look at this with violet, where am I at? And if I now change it to violet, you could see that they're going farther. So if I just compare these guys here, right? So if I come in here and I go back to my screen here, if I now go put this in, right? Here's my violet right here. Let me go get my blue here. So if I compare these guys, what you're seeing here is that, look at the difference here. Look at where the violet light is at. It goes all the way to right here. When I look at the blue light, you could see that it's shorter. So this implies here that because these guys are not, they're being stopped sooner, that means that they have less kinetic energy by blue light. Whereas the violet one here, you could see that they move farther, so they travel farther, which means that there's more kinetic energy by violet light. And who would have thought that the color of light would tell you whether, something was going to come out faster or not? I would have thought, right, standing in the sun, the intensity must be the one that's true here. Now, there's another really strange feature here. And the strange feature is that there's no delay of time in ejecting electrons. So if I go back to the applet, what do I mean by that? Well, what you're seeing here is that you're seeing the following thing here. So let's set the intensity equal to 0 here. And we really don't care about this guy right here. Okay, I want to get rid of all these electrons. Now, look at what happens here. If I turn the light on, what happens? Electrons come off right away. That's a problem. Because let me ask you this question. If you're standing in the sun and it's a hot day, do you immediately get into the sun and get a sunburn right away? Do you instantly go, I got a sunburn right away. I shouldn't have walked outside today.
Yeah, I believe so. I think that it begins immediately.
Really? You don't have to stay out there and absorb enough of the waves?
No, I don't. I think that the radiation damage to your skin is proportional to the amount of time you spend in the sun.
But not
Which
with the
means-
wave model of light, right? Because the wave is a spread out floppy thing. And that spread out floppy thing has to be absorbed proportional to your area. So if you think about it this way, let's think about it this way, Jason. So when we talk about a sunburn, I'm assuming that, let's say that this is your skin here. And then you have some cell right here. So when I think about a sunburn, what I really think about here is that this cell here is going to get damaged. So you could imagine, right? Since the sun is mostly green light, you could imagine I have this green light coming at you, but that green light is coming how? Light is coming in these waves that are spread out. So in order for that cell to get damaged, you have to constantly be depositing energy into this little tiny area. And that's got to take time, because the light is not some localized thing, it's something spread out. And the same thing happens with a piece of metal. So if I have a piece of metal, and then I'm shining light on this thing in a very similar way, when that light comes in, it's spread out. So as it's spread out, what do I have? I have this little electron right there. And that little electron has to absorb the energy and then eject it. And that should take time. It should never be instantaneous.